Over the Baltic Sea, March 1982, a Soviet PVO Strany interceptor station tracked an inbound radar signature moving at speeds that defied standard expectations of atmospheric physics. The signature registered at 78,000 feet and accelerating beyond Mach 3.2. Ground controllers scrambled a MiG-25 Foxbat from Kalovskaya Air Base, vectoring the pilot toward an intercept window measured in seconds. The pilot throttled his twin Tumansky R-15BD-300 turbojets to maximum afterburner, climbing vertically through 40,000 feet in less than 3 minutes. His instruments screamed warnings about engine temperature exceeding redline thresholds. His altimeter needle spun past 60,000 feet. The cockpit pressurization system struggled to maintain integrity as external atmospheric pressure dropped to near vacuum levels. His RP-25 Smerch radar briefly painted the target, a slender delta shape racing through the stratosphere like a missile with a crew. He armed two R-40 missiles, each weighing over 450 kilograms and capable of reaching speeds exceeding Mach 5 in optimal conditions. He locked on. The fire control computer calculated intercept geometry, but the closure rate was impossible. The target was not slowing down, it was pulling away. The American reconnaissance aircraft maintained Mach 3.2 in sustained cruise, while the MiG-25 struggled to exceed Mach 2.8 without destroying its own engines. Within 90 seconds, the American aircraft had opened the gap to over 30 miles and disappeared from Soviet airspace entirely. The MiG-25 pilot descended, his engines damaged beyond operational limits, turbine blades warped from thermal stress, compressor sections showing stress fractures that would require complete engine replacement. He knew he had just witnessed the futility of Soviet air defense doctrine against a single American machine, the Lockheed SR-71 Blackbird. This was not an isolated incident. It was a pattern that repeated itself throughout the 1970s and 1980s, a pattern that exposed a fundamental gap in Soviet aerospace capability. For over a decade, Soviet leadership believed they had built the definitive answer to American high-altitude reconnaissance. The MiG-25 Foxbat was designed as a brute force interceptor capable of reaching altitudes and speeds that no other production fighter could match. When it first appeared in Western intelligence reports in the mid-1960s, NATO analysts were alarmed. Satellite photographs from CIA reconnaissance missions showed large fighter-sized aircraft at Soviet test facilities with unusual configurations suggesting extreme performance characteristics. The aircraft specifications seemed to indicate a revolutionary leap in Soviet aerospace engineering. It could reach Mach 2.83 in sustained flight and climb to operational ceilings above 78,000 feet with a weapons load. Its massive RP-25 Smerch radar could detect large bomber targets at ranges exceeding 100 kilometers, an unprecedented capability for a fighter-mounted system at that time. It carried 4 R-40 air-to-air missiles, each weighing over 1,000 pounds and capable of engaging targets at altitudes previously considered safe from interception. The R-40 came in two variants: the R-40R with semi-active radar homing for long-range interception of non-maneuvering targets, and the R-40T with infrared guidance for engaging targets emitting significant heat signatures. Both variants were designed specifically to destroy American strategic bombers like the B-52 Stratofortress and high-altitude reconnaissance aircraft like the U-2. Soviet propaganda described the Foxbat as unstoppable, a steel sentinel that would make American reconnaissance aircraft obsolete. Defense Minister Andrei Grechko publicly stated in 1967 that no Western aircraft could evade Soviet air defenses equipped with the MiG-25. The Soviet air defense forces deployed the Foxbat across strategic zones, particularly along the approaches to sensitive military installations in the Kola Peninsula, where the Northern Fleet's ballistic missile submarine bases were located, the Far East near Vladivostok and Kamchatka, where strategic bomber bases and naval facilities were concentrated, and the southern borders facing NATO forces in Turkey and Western Europe. Pilots were trained to execute high-speed intercepts against fast-moving targets, and doctrine emphasized immediate scrambles to maximize engagement windows. Soviet planners believed they had finally closed the gap, but confidence is a dangerous foundation when built on incomplete data and wishful assumptions about enemy capabilities. The SR-71 Blackbird was not simply another reconnaissance aircraft. It was a revolutionary integration of stealth, speed, sustained high-altitude performance, and operational endurance that represented a quantum leap in aerospace capability. Designed by Clarence Kelly Johnson and the Lockheed Skunk Works under the highly classified Archangel program, the Blackbird first flew in December 1964 and entered operational service with the United States Air Force in January 1966. Its stated maximum speed was Mach 3.2, but unlike the MiG-25, which could only reach such speeds in brief emergency sprints that destroyed its engines, the SR-71 could sustain Mach 3.2 for hours without degradation. This was made possible by its unprecedented Pratt & Whitney J58 axial flow turbojet engines, which functioned as hybrid turboramjets at high speeds. As the aircraft accelerated past Mach 2.2, bypass tubes opened to direct cold inlet air around the engine core and directly into the afterburners, allowing the propulsion system to operate efficiently at speeds and altitudes that would melt conventional turbojets. At maximum cruise speed, approximately 80% of the thrust came from the inlet and afterburner system rather than the turbojet core itself. The J-58's turbine blades were directionally solidified, a manufacturing breakthrough that allowed them to withstand temperatures exceeding 1800 degrees Fahrenheit without warping or failing. The aircraft's fuel JP-7 was specially formulated to remain stable at extreme temperatures and required a chemical igniter system utilizing trithylborane because it was nearly impossible to ignite under normal conditions. The JP-7 had a flash point of 140 degrees Fahrenheit, making it one of the safest aviation fuels ever developed. The Blackbird's titanium airframe, sourced largely through covert supply chains that unknowingly included Soviet suppliers who believed they were selling the material for innocuous industrial applications, could withstand skin temperatures exceeding 600 degrees Fahrenheit during sustained Mach 3 flight. The airframe was designed with expansion joints that allowed the structure to grow by several inches at operational temperature. On the ground, the aircraft leaked fuel from its tanks because the panels had not yet thermally expanded to seal properly. Maintenance crews would place drip pans under the aircraft during ground operations to catch the leaking JP-7. Only at altitude and speed did the SR-71 become fully operational, transforming from a leaking collection of parts into the fastest air-breathing manned aircraft ever built. Its operational ceiling exceeded 85,000 feet, well above the engagement envelopes of most surface-to-air missiles and all contemporary fighter aircraft. Despite its length of 107 feet and wingspan of 55 feet, the Blackbird's radar cross-section was astonishingly small, measured at approximately 10 to 20 square meters from certain angles but reduced to near insignificance from others due to its chined fuselage, canted vertical stabilizers angled inward to deflect radar returns, and radar-absorbent composite materials applied to key surfaces including leading edges and around the engine inlets. This early stealth capability meant that Soviet radar stations often could not detect the SR-71 until it was already deep inside their coverage zones, and by the time air defense systems reacted, the aircraft was already accelerating away. The combination of speed, altitude, stealth, and endurance made the SR-71 nearly invulnerable to interception. Over 3 decades of operational service, it flew more than 3,551 sorties, many directly over or near Soviet territory, and never once was successfully intercepted or damaged by hostile fire. Not a single SR-71 was lost to enemy action during its entire operational career. Soviet pilots who flew the MiG-25 were among the most skilled and experienced interceptor aviators in the world, but they operated within a system built on the assumption that speed and altitude alone could defeat any adversary. The MiG-25's design philosophy was fundamentally different from that of the SR-71. Where the Blackbird was engineered for sustained high-speed cruise over transcontinental distances, the Foxbat was optimized for rapid climb and short-duration intercepts within Soviet-controlled airspace. Its two Tumansky R-15BD-300 turbojet engines generated a combined thrust of over 44,000 pounds in afterburner, propelling the aircraft to incredible speeds but at a cost. The engines were temperamental and prone to catastrophic failure if pushed beyond their operational limits. The MiG-25's airspeed indicator was redlined at Mach 2.8, and pilots were explicitly instructed not to exceed Mach 2.5 during normal operations in order to preserve engine life and prevent structural damage to the airframe. In emergency situations, pilots could push the aircraft to Mach 2.83, but even this was considered dangerous and required mandatory post-flight inspections. If the MiG-25 exceeded Mach 2.8 for any sustained period, the engines would begin to overspeed, their compressor blades vibrating beyond safe tolerances, and the turbine sections would overheat to the point of structural failure. Once this threshold was crossed, the engines were considered destroyed and required complete replacement, a process that took weeks and consumed enormous resources. Several instances were documented where MiG-25 pilots, attempting to intercept high-speed targets, pushed their aircraft past Mach 3 and caused irreparable engine damage. In one notable case over the Sinai Peninsula in 1971, an Egyptian-based Soviet MiG-25 was tracked by Israeli radar at speeds exceeding Mach 3.2 during an intercept attempt against Israeli F-4E Phantom reconnaissance flights. The aircraft successfully evaded Israeli F-4 Phantoms and outran multiple AIM-7E Sparrow missiles fired at it, but upon landing at an Egyptian air base, both engines were found to have been destroyed by thermal stress and had to be completely scrapped and replaced with new powerplants shipped from the Soviet Union. This was not an isolated incident. Soviet maintenance records indicated that aggressive high-speed intercepts frequently resulted in engine overhauls or replacements, creating significant logistical burdens for units operating the Foxbat. The aircraft's combat radius was severely limited, only around 186 miles at high speed, which meant that pilots had very narrow windows to achieve intercept geometry. If the target was detected late, or if the intercept vector was not perfectly calculated by ground controllers, the MiG-25 would run out of fuel before achieving weapons range. Even when geometry was favorable, the MiG-25's fire control system struggled with high closure rate engagements. The RP-25 Smerch radar, while powerful at 600 kilowatts output, was designed to track large, relatively slow-moving bombers at long range, not nimble or extremely fast reconnaissance aircraft. It lacked look-down, shoot-down capability, meaning that targets flying below the MiG-25's altitude against a ground clutter background were difficult or impossible to engage. More critically, the radar's processing speed could not handle closure rates exceeding Mach 5, which was exactly what occurred during head-on intercepts with the SR-71. Soviet pilots reported that even when they achieved radar lock, the fire control system would lose track of the Blackbird within seconds due to the extreme relative velocity overwhelming the analog processing systems. The R-40 missiles, while long-ranged and powerful with engagement envelopes theoretically extending to 35 kilometers, were designed to engage targets flying at speeds up to Mach 2.5. Against an SR-71 cruising at Mach 3.2 or faster, the missiles simply could not accelerate quickly enough to close the distance before their rocket motors burned out. In tail-chase scenarios, the physics were even more unfavorable. The SR-71's sustained speed meant that even if a MiG-25 launched a missile at maximum range, the Blackbird would simply outrun it, opening the gap until the missile's motor burned out after approximately 15 seconds of powered flight and it fell harmlessly away. Soviet pilots described the experience as chasing a ghost. They would climb to altitude, detect the Blackbird briefly on radar, attempt to vector toward it, and then watch helplessly as the target disappeared from their scopes, accelerating beyond their reach. Ground controllers would vector multiple interceptors toward projected intercept points, but by the time the MiGs arrived, the SR-71 had already passed through and was exiting Soviet airspace. The psychological impact on Soviet air defense crews was profound. They had been trained to believe that no aircraft could evade them, that Soviet technology was equal or superior to anything the Americans could field. But mission after mission proved otherwise. The SR-71 flew with impunity, photographing Soviet missile sites, naval bases, and strategic installations, while Soviet interceptors burned through engines and fuel in futile pursuit. The operational environment of SR-71 missions over or near Soviet territory was meticulously planned and executed with precision that left minimal room for Soviet countermeasures. Mission planners at Strategic Air Command Headquarters and the National Reconnaissance Office analyzed Soviet radar coverage, interceptor response times, surface-to-air missile deployments, and known gaps in air defense networks. They plotted routes that maximized the SR-71's advantages while minimizing exposure to concentrated defenses. Typical missions launched from bases including Kadena Air Base in Okinawa, Japan, RAF Mildenhall in the United Kingdom, and occasionally from Beale Air Force Base in California for missions targeting other regions. A standard reconnaissance sortie over Soviet territory would begin with multiple aerial refuelings, using KC-135Q tankers specially modified to carry JP-7 fuel. The Blackbird would take off with partially filled tanks because its landing gear could not support the weight of a fully fueled aircraft, then immediately rendezvous with tankers to top off its fuel load before accelerating to operational speed and altitude. Crews would conduct pre-mission briefings lasting hours, studying target areas, ingress and egress routes, emergency divert airfields, and contingency procedures for equipment failures or hostile actions. Once airborne and refueled, the SR-71 would accelerate to Mach 3+ and climb to altitudes between 75,000 and 85,000 feet, entering what pilots called the edge of space. At these altitudes, the sky above was black, the curvature of the Earth was clearly visible, and the crew could see weather systems and geographical features spanning hundreds of miles. The reconnaissance systems operator in the rear cockpit would activate the sensor packages, which included optical cameras capable of reading vehicle license plates from 16 miles altitude, side-looking airborne radar that could map terrain and detect moving targets through clouds and darkness, and signals intelligence equipment that intercepted Soviet radar emissions and communications. As the SR-71 approached Soviet airspace, ground-based early warning radars would detect the aircraft and alert air defense command posts. Interceptor bases would scramble MiG-25s and later MiG-31s, vectoring them toward predicted intercept points. Surface-to-air missile batteries would go to full alert status, tracking the Blackbird and preparing to launch. But the SR-71 crew would simply maintain speed and altitude, knowing that no Soviet system could reach them. On some missions, the Blackbird would fly routes deliberately calculated to test Soviet response times and procedures, gathering intelligence on radar coverage and air defense coordination. Soviet pilots would climb desperately toward the Blackbird's altitude, their engines straining, their fuel gauges dropping rapidly, knowing they would never achieve firing position but ordered to attempt interception nonetheless. Multiple MiG-25 pilots reported the frustration of seeing the SR-71 on radar, climbing toward it at maximum performance, and then watching helplessly as the Blackbird maintained a speed and altitude differential that made interception impossible. Ground controllers would provide continuous updates on the target's position, but the information was operationally useless because the MiG-25 lacked the sustained performance to reach the SR-71. In several documented cases, Soviet pilots pushed their aircraft beyond Mach 2.8 in desperate attempts to close the gap, only to suffer catastrophic engine failures that forced emergency landings and resulted in the total loss of the powerplants. If you appreciate discovering Cold War secrets hidden for decades, consider subscribing for future declassified revelations. The defection of Lieutenant Viktor Belenko in September 1976 provided the West with the first comprehensive understanding of the MiG-25's true capabilities, and more importantly, its limitations. Belenko, a 29-year-old Soviet pilot stationed at Chugyevka Air Base near Vladivostok in the Soviet Far East, flew his MiG-25 Foxbat interceptor variant to Hakodate Airport in Hokkaido, Japan, landing with only 30 seconds of fuel remaining after flying at low altitude to avoid radar detection for most of the flight. The defection was not impulsive. Belenko had meticulously planned his escape over several months, waiting for a training sortie that provided him with a full fuel load, and taking the classified technical manuals from the aircraft's document pouch with him, a violation of standing orders that indicated clear premeditation. Japanese authorities, under intense pressure from the Soviet Union to immediately return both the aircraft and the pilot, instead allowed American intelligence officers to conduct a detailed examination under the framework of the U.S.-Japan Security Treaty. Over 67 days, teams from the United States Air Force, the Defense Intelligence Agency, the Central Intelligence Agency, and technical specialists from American aerospace companies disassembled, photographed, measured, and tested every component of the MiG-25. What they discovered was both surprising and revealing. The MiG-25 was not the technological marvel that NATO had feared. It was a brute force design, engineered for a specific mission profile with little regard for versatility or sophistication. The airframe was constructed primarily from nickel-steel alloy, not titanium as had been assumed by Western intelligence. Approximately 80% of the structure was steel, 11% aluminum, and only 9% titanium, used sparingly in heat-critical areas near the engines and along leading edges. This made the aircraft extremely heavy, with an empty weight of over 44,000 pounds, nearly double that of contemporary American fighters like the F-4 Phantom and far heavier than the F-15 Eagle then entering service. The welds were done by hand and the construction quality was functional but crude by Western standards. Rivets were not flush-mounted in many areas, creating additional drag that reduced overall performance. The avionics were based largely on vacuum tube technology, particularly nuvistors and miniature vacuum tubes, rather than solid-state transistors that had become standard in Western military aircraft by the 1970s. While this was initially interpreted as evidence of Soviet technological backwardness, analysts later recognized that vacuum tubes were more resistant to electromagnetic pulse effects from nuclear detonations and temperature extremes, making them more robust in certain operational environments, particularly during nuclear war scenarios where EMP protection was critical. However, the vacuum tube-based systems were also bulky, power-hungry, and limited in processing capability compared to contemporary Western solid-state systems. The RP-25 radar, while immensely powerful at approximately 600 kilowatts, was analog and lacked the discrimination and tracking flexibility of Western pulse Doppler systems that could filter ground clutter and track multiple targets simultaneously. Testing of the engines confirmed what Soviet pilots had reported in debriefings after defecting. The R-15BD-300 turbojets were powerful but fragile. Ground tests conducted by American engineers revealed that sustained operation above Mach 2.8 caused rapid degradation of compressor blades and turbine sections. The engine's low-pressure ratio of just 4.75 at subsonic speeds resulted in abysmal fuel efficiency, which explained the MiG-25's short combat radius and limited loiter time. The maximum G-load rating of the airframe was only 4.5 G, far below the 7 to 9 G limits typical of Western fighters, meaning the MiG-25 could not maneuver aggressively without risking structural failure. One MiG-25 that had inadvertently pulled 11.5 G during a training exercise, when the pilot lost situational awareness during a high-speed dive, was found to have suffered permanent structural deformation throughout the fuselage and wings, and was immediately scrapped. Belenko himself provided invaluable testimony about operational procedures and limitations during extensive debriefings conducted over several months. He confirmed that MiG-25 pilots were under strict orders not to exceed Mach 2.5, except in emergencies defined as imminent attack by enemy strategic bombers, and that exceeding Mach 2.83 would result in mandatory engine replacement regardless of apparent damage. He described intercept attempts against the SR-71 as exercises in frustration and humiliation. Soviet ground controllers would detect the Blackbird on long-range radar systems and scramble MiG-25s from forward bases, but by the time the interceptors reached altitude and entered the engagement zone, the SR-71 was already leaving the area at speeds the Foxbats could not match. Belenko stated that even in ideal conditions, with advance warning and optimal positioning including pre-positioning interceptors at high altitude along predicted SR-71 routes, the MiG-25 could not achieve a firing solution against the Blackbird. The closure rate was too high for head-on intercepts because the combined speeds overwhelmed the fire control computer. The radar could not maintain lock due to processing limitations, and the missiles lacked sufficient speed advantage to catch the target in a stern chase. He recounted that American SR-71 crews seemed to be aware of Soviet intercept attempts and would occasionally alter course or increase speed slightly, almost as if taunting the Soviet pilots and demonstrating their complete tactical superiority. Swedish Air Force radar operators who tracked both SR-71 and MiG-25 flights over the Baltic Sea in the 1980s during reconnaissance missions targeting Soviet naval facilities in the Kola Peninsula confirmed this dynamic. They observed Soviet interceptors regularly positioned 2 to 3 kilometers behind and several thousand feet below Blackbirds transiting the region, unable to close the gap despite operating at maximum performance. The Swedish reports noted that the MiG-25s would maintain pursuit for a few minutes before breaking off, presumably due to fuel constraints or recognition that the intercept was futile and continuing would only waste fuel and risk engine damage. The intelligence windfall from Belenko's defection led to immediate changes in Soviet air defense doctrine and accelerated development programs. Recognizing that the MiG-25 was fundamentally insufficient against the SR-71, Soviet designers under the Mikoyan Design Bureau accelerated development of the MiG-31 Foxhound, an upgraded interceptor with a more sophisticated pulse Doppler radar capable of tracking multiple targets simultaneously and in look-down scenarios, longer range due to improved fuel efficiency, better aerodynamic design, and a two-seat configuration that included a dedicated weapons systems officer to manage the complex sensor and weapons systems. The MiG-31, which entered service in 1981, represented a significant improvement over the MiG-25 in almost every performance metric except raw top speed. But by then the SR-71 had been operating with complete impunity for over 15 years, and had already collected the vast majority of strategic intelligence on Soviet military capabilities that it would gather during the Cold War. The operational record of the SR-71 against Soviet air defenses is a testament to the strategic value of technological superiority maintained through continuous innovation and operational excellence. Between 1966 and 1990, the Blackbird conducted reconnaissance missions over or near Soviet territory on a regular basis, collecting intelligence on missile deployments including SS-18 Satan and SS-20 Pioneer intermediate-range ballistic missiles, submarine bases in the Kola Peninsula and Kamchatka, where Delta and Typhoon-class ballistic missile submarines operated, bomber airfields hosting two 95 Bear and two 160 Blackjack strategic bombers, and strategic infrastructure including command and control facilities, radar installations, and nuclear weapons storage sites. The aircraft typically flew pre-planned routes that took advantage of its speed and altitude to minimize exposure to air defense systems while maximizing intelligence collection. Mission planners used detailed intelligence on Soviet radar coverage derived from signals intelligence in previous reconnaissance missions, interceptor response times calculated from observed scramble procedures, and known gaps in air defense networks to plot ingress and egress corridors that maximize the aircraft's survivability. Even when Soviet defenses were fully alert and prepared with advance warning, they could not stop the SR-71. In several documented incidents, Soviet air defense forces launched surface-to-air missiles at the Blackbird, but none ever came close to hitting it. The SR-71's combination of small radar cross-section from certain angles, extreme speed sustained over long periods, and high altitude beyond the kinematic reach of most missiles meant that by the time a missile was launched, the aircraft was already accelerating away or had passed beyond the missile's engagement envelope. SA-2 Guideline and SA-5 Gammon missiles, the most capable Soviet strategic air defense systems of the era, had maximum speeds of approximately Mach 3.5, but they required time to boost to speed and altitude after launch. The SR-71, already at Mach 3.2 and 80,000 feet when detected, was a nearly impossible target. Missile operators reported that their systems would achieve lock-on fire and then watch as the target simply outran the intercept, with the missile falling away after its motor burned out without achieving proximity. On multiple occasions documented in declassified mission reports, SR-71 crews reported observing missile launches from their cockpits, tracking the trails as the missiles climbed desperately toward them, and then watching the missiles fall away harmlessly as they ran out of energy well below the Blackbird's altitude. The psychological effect of these repeated failures on Soviet air defense personnel was significant and contributed to a broader demoralization within Soviet military circles. They had invested enormous resources spanning decades in building a multi-layered defense system designed to protect the Soviet Union from American air attack, employing thousands of interceptor aircraft, tens of thousands of surface-to-air missiles, and hundreds of radar stations. And yet a single reconnaissance aircraft could penetrate that system at will. The SR-71 flew over Soviet naval facilities in the Kola Peninsula, photographing submarine pens and shipyards with sufficient resolution to identify specific submarine classes and construction progress. It transited the Baltic region repeatedly, collecting signals intelligence on radar installations and communications networks that revealed Soviet air defense coordination procedures. It monitored Soviet bomber bases in the Far East near Vladivostok and on the Kamchatka Peninsula, tracking deployment patterns and readiness levels. It photographed missile deployments in Central Asia and along the Chinese border. Every mission demonstrated that Soviet air defenses were fundamentally incapable of stopping the Blackbird regardless of preparation or resources committed. The frustration was compounded by the fact that Soviet intelligence knew exactly what the SR-71 was doing. They could track it on radar with long-range early warning systems. They knew when it was coming based on observed patterns and intelligence from sources within NATO countries, and they could predict its approximate routes based on strategic intelligence targets. But none of that mattered. Knowledge without the capability to act was worse than ignorance. It reinforced the perception that the Soviet Union was technologically inferior, that for all its military might and nuclear arsenal, it could not protect its own airspace from a single American aircraft operated by two-man crews. In 1981, a Swedish Air Force JA-37 Viggen fighter managed to achieve a radar lock on an SR-71 during a training intercept over the Baltic Sea, the only non-American fighter ever documented to do so during the Cold War. However, this was accomplished under highly controlled conditions, with advanced knowledge of the SR-71's exact route provided through NATO coordination channels, and with the cooperation of the American crew, who were not actively evading and maintained steady course and speed to allow the Swedish pilots to demonstrate their capability. The Swedish pilots deserve credit for their skill and precision in executing a difficult intercept, but the exercise occurred in a non-hostile environment where the Blackbird was not taking defensive measures or employing its full performance envelope. In contrast, every Soviet intercept attempt was conducted in a hostile environment where the SR-71 crews were actively evading, varying altitude and speed, and employing electronic countermeasures. And not a single Soviet pilot ever achieved a weapons-quality lock on the aircraft sufficient to launch a missile with reasonable probability of intercept. Years later, Captain Mikhail Myagkey, a Soviet MiG-31 Foxhound pilot, claimed in post-Cold War interviews that he had successfully locked onto an SR-71 in the late 1980s during a mission over the Barents Sea, but chose not to fire because the aircraft had not technically violated Soviet airspace, and he lacked authorization to engage. This account has never been corroborated by American sources or declassified Soviet military records, and given the Soviet Union's documented willingness to shoot down aircraft that strayed into their airspace, including the tragic downing of Korean Airlines Flight 7 in September 1983, which killed all 269 passengers and crew, the claim is treated with considerable skepticism by Western military analysts. It is far more likely that if a Soviet pilot had achieved a valid firing solution against an SR-71, they would have received immediate authorization to take the shot and would have done so. The fact that no SR-71 was ever damaged or destroyed by Soviet air defenses despite thousands of attempted intercepts is the strongest evidence that no such opportunity ever existed. Join us here at Classified Warfare as we uncover the operations and technologies that kept the world on the brink.